Bismillah ar-Rahman ar-Rahim. Let's talk about the logic gates. You know, the digital circuits which we want to build. For example, you want to build the processor, you want to build the RAM, or any device for that matter. It's made up of the gates, okay? And now, if you have a gate, and we call them the logic gates. Why we call them the logic? Because they are like two-state devices where we have a two states, kind of an on and off. Like we have bulb, which is either on or off, right? If we have a bulb which is on or off, so it is a two-state device. So anything which is used as two-state device is called as a we can apply the logic on that. For example, if we have a CD, how we write on a CD, how a movie or a song is on a compact disc or a DVD. We have there are two states in the terms of pits and lands. That means we, using a laser, create a little hole, little deeper pit on that, or if we leave it, so that's called the land. Okay, the pit may be represented by 0 and land represents 1. So your DVD is actually having little holes, the microscopic holes created by that laser. And if you have a hole, that is a 0. If you don't have a hole, that's called a land. So this is how we represent the logic. In case of the electronic gates, we use the voltage. We use 0 volt for 0 and 5 volt for 1. Okay, okay, this is also called the positive logic. Okay, so we have an inputs where we have these voltages, and we have outputs where we receive these voltages, 0 volt for 0 and 5 volt for 1. Okay, and there may be some time delay between the gate that you have put the input done input of the gate and the output is coming. There will be some subtle delay. Okay, now the first gate is the easy gate, is the AND gate. AND gate is the symbol is like this. Okay, so what we do in an AND gate is, if both the inputs are 1, and only then output is 1. Rest, if one of them is 0, if one of the inputs is 0, output is gonna be 0. So in this is called as a truth table. And in a truth table, if both the inputs are 1, only in that case we will have the output 1. And in the OR gate, if one of the inputs is 1, okay, other may be 0. In the AND, if one of the input is 0, output is going to be 0. And only case is if one of the inputs is 1, if both of the inputs are 1, then it was 1 in the AND gate. But in the OR gate, if at least one of the inputs is 1, output is going to be 1. So here one of the input is 1, one of the input is 1, 1, 1, both are 1 here, output is 1. Only case 0, when both of the inputs are 0, output is 0. Now the NOT gate. The NOT is a complement gate. Means if input is 1, output is gonna be 0, or if it is 0, output is gonna be 1. So ये उल्टा करेगा, 0 को 1 बनाएगा, 1 को 0 बनाएगा, ठीक है ना? You can use the AND gate also to implement the NOT gate by A को खुद को ही देना, AND gate को दूंगा मैं 2 बार खुद को ही और उसको NOT करूंगा. मान लीजिए फर्ज कीजिए A 1 था. So when it is 1, this is also 1, क्योंकि A में दोनों तरफ से input 1 दे रहा हूँ मैं AND gate को. 2 इनपुट एंड गेट है, तो 1 and 1 एंड गेट 1 देगा, लेकिन नॉट इसका 0 बनाएगा, सो आउटपुट विल बी 0. So if the A was 1, output will be 0. Now if A will be 0 and 0 to the AND gate becomes 0, and not जो यहाँ पे bubble है, ये not इसका करेगा, complement करेगा, so 0 को 1 बनाएगा, so output will be 1. So if input is 0, output will be 1. If input is 1, output will be 0. और दूसरा तरीका है कि आपने A दिया AND gate को, NAND gate को, in fact it's not an AND, it's a NAND gate, means and not, bubble है ना यहाँ पे not. So A और 1, यानी कि ये तो 1 हमेशा रहेगा. अगर A 1 है, 1 and 1, again AND gate will make it 1 and not इसका 0 बनाएगा, so that means output will be 0. If this is 0 and 1, AND gate क्या बनाएगा इसका 0 बनाएगा, लेकिन NOT gate इसका 1 बनाएगा, so output will be 1. That means अगर input A 0 था, output will be 1, so it is the functionality of the NOT gate. Okay, now NAND gate is simply the inverse of the AND. So that means you put up a bubble on the back of an AND gate, so whatever the AND gate gives, it negates that. Because if we had a 0 0 0 1 1 0 1 1, this is the A and this is the B, and output, if we see the output, we know AND is only 1 when both are 1, rest are 0. So what will NAND do? So this is A and B. What is the A and B inverse? Okay, A and B complement. So NAND is A and B complement. So that means whatever the output of AND is, do inverse of that. If it is 1, make it 0. If it is 0, make it 1. 0 1 0 1. So that will be 1 1 1 0. That's going to be the NAND. That's what is here, the AND ka ulta. So you have an AND gate and put a bubble on the back to make it a NAND, means inverse of AND. That means AND followed by a NOT, the bubble. Similarly, we have what is called as a NOR gate. The NOR is the NOT of the OR. So whatever the OR is, put in the NOR. So if we have the two inputs A and B, that is 0 0 0 1 1 0 1 1. So what is A or B? So A or B is nothing but if one of the inputs is 1. So here I'm seeing another input is 1, output is going to be 1. One of the inputs is 1 1. Both here inputs are 1, so it is 1. Only case when both are 0, it will be 0. So what will be A or B complement? That is NOR. So NOR is the inverse of OR. So whatever the OR has done, it is 0, so make it 1. If it is 1, it is 0 1 0 1 0. That is what is here. So that's A or B complement. Okay. Now the next one which we'll be using for our adder circuits and all is the XOR gate. Okay, it's a very powerful gate. It's written as either the XOR or simply XOR like this. Okay, or sometimes you write it EXOR, XOR, or you write it XOR simply. Okay, it is like this. So the diagram is you have a OR gate like this, but you put up another curve here in the front that makes it XOR, because this was your AND, okay, and this is your OR, okay, and this is your XOR. So what is XOR doing? And we show it like this: A XOR B. That's XOR is shown by the circle and the plus in between. Okay, so XOR में अब ये याद रखें आप कि when both the inputs are same, like it is 0, it is also 0, the output will be 0. Here also 1, it is also 1. So both inputs are same, output is going to be 0. If one of the inputs is high and another is low, then output is 1. Only this case, it is 1. Okay, remember this thing is very important for our adder circuit, and I'm making this video for you so that there will be no issues while discussing the adder circuit. Okay, otherwise it's very simple and you must be knowing it. I know you must be knowing it, but I'm just making it to make it sure that everybody is on track. Okay, so this is the XOR. Okay, and whatever is the XOR complement, okay, like we had an AND complement, then we had a NAND and NAND complement. Sorry, we have an OR complement means NOR. XOR complement, okay, will be called as XNOR. Now, so that means if we had an XOR, we know XOR, what was the truth table? 0 0 0 1 1 0 1 1, and we know when there is one of the inputs is high, it's gonna be high. Okay, but if both the inputs are same, it's gonna be 0. Both the inputs same, it's gonna be 0. And do the inverse of it. That means 1 0 0 1. So now this one is my A XOR B complement, and is also called as equivalence, shown by like this. B, you can use it like this, called equivalence. Okay, either you say A XOR B whole complement, or you say A equivalence B. That's same, one of the same thing. That means you are doing not to the XOR, or circuit wise you put up a XOR gate, this is XOR gate, and put a bubble there. That means not to the what, XOR. So that's called XNOR. You can write it like this, XNOR, or sometimes you write it like this, XNOR. Okay, keep these things in mind, and we may be also making a video about the how these gates are created, what logic. There are 3 types of logic which we may discuss in the next vid. So until the next time, ma salama.